Hello guys, my name is Lazaro and today we're going to be doing a medium LeetCode problem. This problem is called sum of nodes with even valued grandparents. Given a binary tree, return the sum of values of nodes with even valued grandparents. A grandparent of a node is the parent of its parent, if it exists. If there are no nodes with an even valued parent, return 0. So in this first example right here, we have a 6 as the root, and now if we were to try to find the grandparent of this 6, we have to go to its parent, and since its parent doesn't exist, that means there isn't any grandparent. So 6 doesn't have a grandparent, and we continue. Looking at 7, 7 has a parent, but a grandparent is defined as a parent of a parent. So the parent of this 7 needs to have a parent as well, which since the parent of 7 is 6, and 6 doesn't have a parent, 7 does not have a grandparent. Now, to make this a little bit less confusing, from now on, a little pattern we can notice is since a grandparent is a parent of a parent, that means a grandparent is 2 nodes above the current node we're looking at. For example, let's look at this 2 down here. This 2 has a parent, and this 2's parent also has a parent. So the grandparent of this 2 is 6. AKA, if we were looking at 2, and we go 2 nodes up, so 1, 2, we end at the grandparent. And this little trick is going to come in handy when we write out the logic and the code for this problem. So looking from going to 2, all we have to look is if we were to go 2 levels higher, is there a node? And since there is, that means this 2 has a grandparent. So let's get that node that's 2 levels higher, and let's check if it is even. 6 is even. Since it is even, we add 2 to our tally. Now the same thing goes for 7. We can go 2 nodes up and it exists, and 6 is even. So now we do 2 plus 7, which is 9. Now over here on this side, actually let me go over 9. 2 levels higher than 9, or 2 nodes higher than 9, will put us at 7. So 7 is a grandparent of 9, but 7 is odd. Which is why we don't add 9 to our tally. Same thing goes for 1 and 4. Their parent is 7, but 7 is still odd. Now at 1, we go 2 nodes higher. We have 6. Therefore, we add it to our tally. Now we do 9 plus 1, so which will give us 10. So 7 plus 2 plus 1 will give us 10. Now when we look at 3, is the exact same thing. We're on 6, 2 nodes higher, and 6 is even, so we add 3 to our tally. Now we have 13. Now finally we're on 5. 5 also has a grandparent because if we go 2 nodes higher, we're at 8. And 8 is even, so we add 5 to our tally as well, and that's how we end up with 18. So that took a while, but now that we read the description and looked at the example, let's actually start working on the logic for this question. So right here I wrote out the tree, and now let's discuss the main logic that we use to understand that example and that we're going to be using for our code. So what we want to do is, since we know a grandparent is usually going to be 2 nodes higher than the current node we're looking at, we want to keep track of number 1. Let me write this here. Keep track. The first thing we want to keep track is the current level we're at. So for example, if we were looking at this 6, our current level would be 1. If we were looking at this 7 or 8, our current level will be 2. If we were looking at 2, 7, 1, or 3, anything here, our current level will be 3. And if we were looking at 9, 1, 4, 5, our current level will be 4. So that's the first thing we want to keep track of, which will be extremely easy when we write out the code, because since we're going to be traversing this tree, every time we go to the left or to the right, we're going to be incrementing this counter by 1. So for example, once I move from this 6 to the left, I need to do 1 plus 1 will give us 2. And now I'm here on the 7, whether I go to the left or to the right, I'm going 1 level deeper, so I still need to increment it and go from 2 to 3. So that's super simple. We've done that in past videos. Now the second thing is we want to keep track of the nodes at every level. We want to keep track of this to find the grandparent. For example, if I'm at 2 and I know my current level is 3, I want to find the node that's at the level 3 minus 2, which will give me 1. I want to find the node that is at 1. And if there's a node at level 1, that means this 2 has a grandparent. And if this 2 has a grandparent, then we just have to check the value of that node at level 1 to see if it's even or odd. And that's all we need to solve this question. Now, how can we keep track of these things? Well, to keep track of the nodes at every level, we're going to be using a hash map. Let me write it here. Hash map. So for example, if this was my hash map right here, at level 1, I have a 6. At level 2, I have a 7. Now this hash map, as we traverse, this hash map is going to be updating as we traverse the tree. So for example, in the beginning, at level 1, we're going to insert the 6. When we go to the left of this 6, when we visit its left node, hash map is going to update to 1, 6, and then 2, 7. 2, where the key is the level or the depth, and the value is going to be the value of the node. And then over here on the right side, it's going to be 1, 6, 2, 7. Keep in mind this 8 doesn't have the level 7, doesn't have node value 7 at level 2. And the reason for that is because it can't access 7. 7 is only a sibling, and we only want to keep track of parents. And since a node can only have one parent, then we know that we're only going to have one value in this for every key in this hash map. For example, let's say I'm here in the 5. I'm going to have 1, 6, 2, oh, I actually messed this up. It's not 2, 7, it's 2, 8. Sorry about that. I was explaining why it's not 2, 7, and I actually wrote 2, 7. There we go. Oh my god, I did it again. Okay, there we go. That's way better. Alright, so for example, if we were at this 5, our hash map would look like this. 1, 6, 2, 8, 3, 3, and then 4, 5. Since we know this 5 is at level 4, if we were to do level 4 minus 2, that will give us 2, which is the level of our grandparents. And if we were to access 2 from this hash map, we will get 8, which is the grandparent of 5, and that is indeed correct. So from there, all we have to do is check if 8 is even by checking if modulo 2 of 8 or 2 modulo 2 is 0. Or 8 modulo 2 is 0. And if it is, then we want to add it to our tally. And that's the exact logic of our code. So now that we've talked through this, let's write out how that code would look like. Let me first expand my canvas size. Perfect. Cool. So let's write out this code. We already know we want to keep track of a variable to hold our answer. And then we also know that we want to traverse this tree in a depth first search order. I personally like depth first search. You can probably do this with a breadth first search, but I'm gonna do it with depth first search. And I'm also gonna be doing this recursively. Depth first search can be done recursively or with a stack, but I'm going to do it recursive. So we have our node. Now something else we need to keep track of is the current depth we're at, and then also all the depths all the depth mappings where the key is going to be the depth and the value is going to be the node value at that depth. So let's call it depth mapping. Pretty long, but that's fine. Perfect. Now, if we're adding node, if our node exists, because we don't want to do this, for example, these nodes, these leaves down here of the tree, we don't want to do our logic for nodes that are empty and that are null. We only want to work with nodes that actually exist. So if our node does exist, then let's add this node to our depth mapping, and let's add this current node that we're at, let's add it to the depth mapping where the key is its depth and the value is the node value. Now let's see. So to check if it does have a grandparent, we have to go 2 nodes higher up. And to basically going 2 nodes higher up is doing depth minus 2, checking if it's in our depth mapping. So if depth minus 2 is in our depth mapping, then we know that we have seen a node at that depth. So it does have a grandparent. The current node we're on, it does have a grandparent. So if that's the case, then we want to check for something else. We want to do if the node value at that depth, if that's even, then we want to add it to our answer. So if it's even, let's add it to our answer and let's keep track of it. Now outside of this if statement, let's continue with our depth first search by going left, passing it our depth, but incrementing it by 1 because we're going deeper. Then let's also pass it our depth mapping. Now we're going to do the exact same thing, but we're going to go to the right and explore the right subtree of the current node we're on. Still incrementing the depth by 1 and still passing it our depth mapping. And that's all we have to do for this depth first search, for this tree traversal, and to keep track of our tally right here. That's all we have to do. Now outside of this function, let's actually call it. Let's pass it the root. Let's pass it a depth of starting at 1, and let's pass it an empty hash map. Then let's return our answer. And this code right here does everything we just talked about. So now let's write out this code and see if it actually works. Because we're keeping track of the tally and we're only adding to, why did I put 0? Oh my god, I'm going insane today. So instead of just adding 0, we want to our answer add node.val. There we go. Okay, I have no idea why I did 0. I think I was looking at this 0 right here. But I'm glad I caught it. You guys probably caught it first to me and were thinking, wow, this guy's going insane. But all right, So with this function, we're traversing the tree, and then we're updating our tree, our depth mapping, where the key is a depth and the value is the node value at that depth. Now we can tell if a node has a grandparent, where if we were to take the current depth of that node and subtract 2, if that depth minus 2 value is in our depth mapping, that means we've seen a node at that depth before. Now, if we get that node at depth minus 2, and if that node value is even, we want to add it to our answer. And then, of course, continue traversing the tree with these 2 statements right there. And then, at the end, call that actual function to do the traversing, and you just return answer. So now, let's write this code. So let's first create that variable, initialize it to 0, and now let's create our function. Oh, I also noticed I call this DEF instead of doing a little bit more pseudocode key and calling it something like function. But that's right, no big deal. And now let's create our we want to take in our node, we want to take in our depth, and we want to take in our depth mapping. Now, if I'm typing a little bit slow, please bear with me. I got a new keyboard, and I'm still learning it. Now, if that node exists, then let's add it to our mapping, where the key is the depth we saw it at, or it's currently at, and then the value is the value of the node. Now, if depth minus 2 is in our depth mapping, and if that node value at depth minus 2, if that is even, which we can check by, where's my, there we go. Okay, which we can check by just doing the modulo of 2. So if it is even, then we want to increment our answer variable by that node value. Else, we do nothing and we just continue traversing the tree. Plus 1 to increment its depth, and then also pass it the depth mapping, which this is going to give me an error right here. There we go. Now we do the exact same thing with this, but instead of going to the left, we now go to the right. Oh, I'm on Mac, it's not. There we go. So now instead of going left, we go right. And then that's all we really need for this function. What else we need to do is just actually call the function, pass it roots, pass it depth of 1, and then pass it an empty hash map or dictionary, which is called in Python. And then let's just return self.ans. Now let's see if I made any typos. Okay, I actually didn't. And now let's submit and see if we get it right. And we do, perfect. So if you guys enjoyed this video, I highly recommend you guys join our Discord server where we send out these beginner and advanced problems. And we also do these videos to explain the solutions to them. Now, something I do want to add is that the time complexity of this problem is big O of n, because we have to go through every single node in the tree, and its space complexity is also big O of n, because worst case scenario, we only have a tree that's only going left or only going right, and we have to add every single node to our hash map. Something else I do want to add is that there is a way, a very greedy way, of doing this in big O of n time complexity, but big O of 1 space complexity, where you use a whole bunch of if statements. But of course, I did it a little bit neater way and giving up some space. But I do just want to let you guys know that, and I'll leave it as an exercise for you guys to implement that. If you guys actually do implement it, then click and it's accepted. Then right click on accepted, and then get this link and put it in the comment section down below. Other than that, I hope you guys did enjoy the video. I'm sorry for having so many mess ups. I'm glad I did catch them. At least I think I caught all of them. But yeah, hope you guys enjoyed, and thank you for watching.